In this video, we solve problem 7.5.014 from the Larson and Edwards Calculus Early Transcendental Functions text, 7th edition. We're asked to use Hooke's law to determine the work done by a variable force in a spring problem. And then we're told that 5 joules of work is required to stretch a spring, 0.5 meter from its original length. Then we're asked to find the work required to stretch the spring an additional 0.2 meter. So this is the idea. If you have a spring, let's say this is its natural length, we'll call that x equals 0. If you pull the spring, this way, there's going to be a force that, let's say we pull it a little bit farther. So we pull it this way. There's going to be a force that wants to restore that spring to its original position. And that force is given by k times x, where x is that distance that spring has been stretched from its rest position right here. And typically, this is given by negative k times x because it's always going in the opposite direction. So yeah, we'll say negative kx. So now in this problem, we're told that 5 joules of work is required to stretch a spring 0.5 meters from its natural length. So we're going to use this to find our spring constant k. K is a property of the spring. So let's just set up the work. Now the work is, the work on one little piece of the spring is force acting on that little piece times the distance it moves through. Now if we're talking about a spring, the force depends on how far we are from that rest position, x equals 0. So that force would generally be negative k times the x value, and that force is only acting for a tiny little distance. And because then once you're at a new position, you're going to get a different force. And once you're at a new position, you'll get a different force if you're pulling it this way, just for example. We would also have a restoring force if we were compressing that spring here. It would have a tendency to want to go back that way. But the displacement that little force acts over is just given by delta x sub I. So that's just a little tiny interval. And then if I want the total work done, it turns out we'll just take the limit as the number of pieces goes to infinity of the sum of the work on each piece. And that's the same as this limit as the number of pieces goes to infinity of the sum as I goes from 1 to n of w sub I. So that's the work on one piece, and we're just adding those up. And that work on one piece is given by this negative k times x sub I times delta x. And that is a very special case of the definition of an integral. So this is equal to the integral of negative kx with respect to x. And we'll integrate from x equals some value to x equals some other value. Now let's look at what this is, what the problem statement says over here. It says 5 joules of work is required to stretch a spring from 0.5 meters from its natural length. So its natural length is x equals 0, and then we're going to stretch it to x equals 0.5 meter. So we're going to integrate from 0 to 0.5. And we'll get, for anti-differentiating with respect to x, we get x squared over 2 times that negative k. And then you evaluate this at 0 and 0.5 and subtract. So we have negative k times 0.5 squared over 2. That's 1/2 squared, or 1/4 over 2. So we get negative k over 8 That's what we get when we evaluate at x equals 0, x equals 0.5, at x equals 0, we just get 0. And so we would get this, negative k over 8. Actually, I think the way that this problem is set up, we're assuming that even though that force is restorative and is typically denoted this way with that negative out front, it looks like they're not including that sign at all. So we will just change that to a positive, and that's okay. And I really don't mean plus k over 8, I just mean positive k over 8. Some people are going to get me on notation about that, but I hope you understand that's just k over 8. That's the work done by this force. And so if I want to find the value of k, and I know that the work done is 5 joules, I can set this equal to 5, and then we'll multiply. So k will equal 5 times 8, which is 40. Okay, so that's our k. So now we know that this is a property of this particular spring. K is equal to 40, and the force is equal to 40 times x if we aren't concerned about that sign on that restorative force. Okay, now we're asked to find the work required to stretch the spring just a little bit more. So we're going from 0.5 meters to 0.2 meters. So the question is, how much work is required to get us from here at 0.5 to here at x equals 0.7 meters? Well, we're just going to do the same thing that we just did a second ago. Work is the integral of force times the displacement that's acting over, and that's going to be delta x. So we're just using force and distance here because we're in calculus and the force and the displacement are acting in the same direction. We're not too worried about the sign. And then we want to integrate this from x equals 0.5 to x equals 0.7. So this isn't too bad. We just bring the 40 down, add 1 to the exponent, divide by the new exponent, evaluate at 0.5 and 0.7, and subtract. 40 divided by 2 is 20. I guess I was doing that in my head. So I've got 20x squared evaluated from 0.5 to 0.7. So you're going to have 20 times 0.7 squared minus 0.5 squared. So I think we'll have 20 times 0.49 minus 0.25. So that's 20 times 0.24. And then if we multiply by 20, that's going to give us 4.8. And we were measuring work in joules over here, so this is going to be work in joules as well. So I think that answers the question. The question said, find the work required to stretch the spring an additional 0.2 meter, and we're going from 0.5 to 0.7, and so that's that. It gives us the right answer.